All right, class. Today what I'm going to do is a quick review on trig. The problem with trig is that you can, and you often do, you can have an entire semester class devoted to all the things in trig, and in fact you could spend a whole year on material. I mean, there's so much there. It's very deep. So this is just going to be a very quick brush up on some things that you should just know, just a little bit of review. What I find is a lot of students, they'll be working a problem and they'll get down to something like this, the problem equals sine of pi, and then they don't know what to do, and it's almost as if the trig function itself trips them up. It makes them freak out or something. There's really no reason to freak out when you see trig functions. In fact, sine of pi is just 0, and you can move on, right? It's just, there's a lot of things to keep track of, and a lot of people just don't remember all the things that they should. And so this would be a bit of a brush up. And at the very least here, I mean, you could at least plug it into your calculator and see what you get, right? I mean, so anyway, the first thing to note about trig functions is that they're they're quite different than what we're used to when we talk about functions, right? Usually functions are things like x squared. You're taking x and it's giving you, you're doing something to it, right? You're squaring it or taking the square root or e to the x or whatever. Trig functions are quite different because what they do is they're based on the unit circle. Now, a lot of people don't really realize this, but if you take the unit circle centered at the origin, 0, 0, and you look at any angle theta. Well, any angle theta, its terminal side is going to intersect the unit circle at a point xy, right? There's a point, and there's the x value and the y value. And basically all we do is we develop some functions based on this. In fact, we say sine of theta. Okay, we just say it's the y coordinate. Okay, and we say that cosine is the x coordinate. And that's it. So it's very different because what happens is we give sine and cosine an angle, and it tells us the coordinate of this point xy that the terminal side of that angle intersects. So this point xy we could actually rewrite as cosine theta comma sine theta. Right? It just gives us sine and cosine gives us the coordinates, xy coordinates of this point that is generated from this angle. Okay? That is what, that's all trig functions really are. And we have a third main one that we call tangent of theta, which is y over x. It's the ratio of these two coordinates. Okay? It's the ratio function. Okay, and so that is the basic definition of the trig functions, and we can extend it further because if you think about this, we can actually make a right triangle out of what we just made there. Okay. And we can extend it to circles of any radius, not just radius 1. Okay. So here is a little more information. If you can see this, here, let me get a little closer with this. Over here is our right triangle definitions that most people are familiar with, right? Those are the ones that most people actually know, right? If you have the adjacent side, the opposite side, and the hypotenuse, So sine of theta is opposite over hypotenuse, tangent of theta is opposite over adjacent, cosine is adjacent over hypotenuse. These are the things that most people recognize as the trig definitions. But the problem is there's some issues with it because, like, for example, can you make a right triangle with a theta of, like, 270 degrees? Well, sort of, in doing it this way, but you've got to be kind of careful. And what about 0, right? You don't really have a triangle anymore at that point if you're looking at theta equal to 0. Further, we can extend it to a circle of any radius r. And all we do is sine becomes y over r, cosine becomes x over r, etc. All right, we will be using radians for almost everything in this class, and that's going to be true for physics. Radians just work out really well, and we're about to see in just 1 second how well radians actually work out and why they're so nice. Students tend to hate radians when they first see them, but I promise you radians are just mathematically a much nicer way to deal with things than degrees. Right? Degrees make sense for many kind of construction examples and whatnot, but for most things that we'll be playing with, radians are just going to be the best. And here are your unit conversions. Basically, 180 degrees is equal to pi radians. Okay, so here is the unit circle, right? And if we think about this in terms of our usual trig definitions, we can see, say, at the angle 30 degrees, which is pi over 6 radians, right, that terminal side of the angle crosses at the point on the unit circle, or intersects the unit circle at the point square root of 3 over 2, comma 1/2. That should seem fairly familiar. 60 degrees, that's pi over 3. The terminal side of that angle intersects the unit circle at 1/2, comma, square root of 3 over 2, and so on and so forth. So, for example, if I wanted to find sine of, let's say, 5 pi over 6, okay, using the unit circle, I would go and look for 5 pi over 6, which is right here, right, and then remember, sine, remember our definition is the y-coordinate. So sine, okay, of 5 pi over 6 is going to be 1/2. Whereas cosine of 5 pi over 6, well, we're going to look at the x-coordinate, which is negative square root of 3 over 2. Okay. Okay. Now, one thing to note about this, some people just have the entire unit circle memorized. And I mean, that's okay. If you do, that's great. But if you don't, what I pretty much submit is that you really only need to know this first quadrant, right? One thing to notice is, check this out. I have pi over 6 here, and that gives me the point square root of 3 over 2, comma 1/2. Now, if I look at every other something pi over 6, like 5 pi over 6, 7 pi over 6, 11 pi over 6, well, what happens is I basically have the exact same point for all of these, right? Because for pi over 6, it's square root of 3 over 2, comma 1/2. For 5 pi over 6, it's negative square root of 3 over 2, comma 1/2. For 7 pi over 6, it's negative, but the same numbers. And for 11 pi over 6, it's positive negative. So we have the same numbers, the same magnitudes, only the signs are changing. Okay, only the signs are changing. So if we know, okay, the first quadrant, well, basically we can find sine or cosine of pretty much any other angle. We just have to be aware of what quadrant we're in. Okay, so in other words, if I have, I'm going to write it like this: sine of k pi over 6, just assuming that, just assuming k does not, divide evenly into 6 to make 6 something else. If it's a something pi over 6 and that's in its, simplest form, this has to be, right, based on what we know, plus or minus 1/2, and which one it's going to be is based on the quadrant. Okay, so if that angle is in quadrant 1, it's going to be positive. Quadrant 2, positive. Quadrant 3, negative, and quadrant 4, negative. Right, so that pretty much means I already know sine of pi over 6, any form of pi over 6, is going to be plus or minus 1/2. And I know that cosine of k pi over 6 is going to be plus or minus the square root of 3 over 2. So it's really just a matter of which quadrant we're in. Okay. Now, from here, there's one more thing that really helps us out, and that is the following pattern. Okay, here are the quadrant 1 values of sine. Right, at 0, sine is 0. Okay, at pi over 6, we get 1/2. Pi over 4, we get square root of 2. Pi over 3, we get square root of 3 over 2. And pi over 2, we get 1. Now, you might not see the pattern yet. Okay, but if I decide to rewrite everything as the square root of something over 2, you'll start to see the pattern. Right, 0, I could rewrite as the square root of 0 over 2. You would never do that, but you could. I could rewrite 1/2 as the square root of 1 over 2. Then, of course, the square root of 2 is square root of 2. Square root of 3 is, of course, square root of 3. I'm not changing anything on these. But then 1, if I rewrite this as the square root of 4 over 2. Now, does that make sense? Well, yeah, the square root of 4 is 2, so 2 over 2 is 1. So the pattern is actually always the square root of something over 2, and it goes in order from 0, 1, 2, 3, 4, and we just simplify the ones that need to be simplified. This is the pattern for sine. And once you know the pattern for sine, you know the pattern for all the sines in any quadrant. You just need to know which quadrant you're in. Okay? Now, this is sine. Well, what about cosine? Well, I submit that once you know the pattern for sine, you also know the pattern for cosine. Just cosine goes backwards, right? 1 is equal to cosine of 0. Square root of 3 over 2 is equal to cosine of pi over 6. Square root of 2 over 2 is equal to cosine of pi over 4. So this is where they match here at pi over 4. They're the same. Cosine is equal to 1/2 at pi over 3, and it's equal to 0 at pi over 2. So cosine follows really the same exact pattern, just backwards. Okay, so once you know the pattern for sine, you also know the pattern for cosine. Okay? And this, I mean, really helps, because once you know this pattern, you pretty much know that, right, that sine of k pi over 4 is going to be plus or minus the square root of 2 over 2, just dependent on the quadrant. Okay, so if we go back to the unit circle, okay, in quadrant 1, both sine and cosine are positive, so both are positive. Quadrant 2, the y's are still positive, but the x's become negative, so that means that cosine here, right, that cosine of theta will be negative in this quadrant. So here's quadrant 1, here's quadrant 2. Okay. Quadrant 3, well, both the x's and the y's are negative, so they're both negative in quadrant 3. Okay. And here in quadrant 4, well, in quadrant 4, the x's are positive, which means cosine is positive, but the y's are now negative, so that means sine of theta is negative in this quadrant. Now, one final thing is, well, how do you know right off the bat which quadrant you're in? I mean, that's a great question. Okay, now I think it's pretty clear when you're in quadrant 1 because you have very basic fractions. They're always pi over 6, pi over 4, pi over 3, pi over 2, 0, you know, no problem. When you're in quadrant 2, does everyone see that? I say that as if there isn't, like there's more than one of you watching this video at a time. Do you see that the number in the numerator here, say 2 pi over 3, 3 pi over 4, 5 pi over 6, is 1 less than the denominator? Right? So it's 2 pi over 3, 3 pi over 4, 5 pi over 6. Okay, so here the number in the numerator is 1 less than the denominator. Quadrant 3, on the other hand, we're 1 more, right? 7 pi over 6, 5 pi over 4, 4 pi over 3. All right, way to go. And then quadrant 4, this one's a little trickier because these two kind of make sense. 1 less, 1 more. Here, 11 pi over 6, 7 pi over 4, 5 pi over 3. These guys are 1 less than double the denominator. So I'll actually write that one down because it's a little trickier. So this is 1 less than double the denominator. Okay. In other words, here's 6. Double 6 would be 12. We're at 11. Here, double 4 would be 8. We're at 7. Double 3 would be 6. We're at 5. Okay, 1 less than double. That's quadrant 4. And if you know you've got it much farther than that, say 13 pi over 6. Well, if you had something like 13 pi over 6, the first thing you'd want to do is subtract 2 pi. Right, get it back. And 2 pi I could rewrite as 12 pi over 6. Right, that's 2 pi in terms of 6. Right, that would simplify down to 2 pi. And that would bring us back to 1 pi over 6, which is quadrant 1. Okay. All right, so let's say you wanted to find something like sine of 4 pi over 3. Okay, well, I know right off the bat this is a pi over 3. It's a 4 pi over 3. But pi over 3 for sine, that's square root of 3 over 2. And I remember that because we get 3 goes to 3. Okay, that's kind of how I keep it in track. And now I need to pick one, right? Which one is it going to be? Well, this is 1 more than the denominator. 1 more than the denominator means Q3. So quadrant 3, both are negative. Right, so this will be negative square root of 3 over 2 because we're in quadrant 3. I always like to do that just to kind of write what's going on. Okay. And how about something like cosine of, let's say, 7 pi over 4. Okay, 7 pi over 4. Well, a pi over 4 situation is always going to be the square root of 2 over 2. Now I just need to know which quadrant we're in. Well, 7 pi over 4, that is quadrant 4, right? And usually that one you can pick up right on because it's way more than the other ones. Right, so 7 pi over 4, we're in quadrant 4. Now cosine is positive in quadrant 4, so we're going to pick positive square root of 2 over 2 since we are in quadrant 4. Okay. Now I pretty much like to tell my students that if you know this, if you know quadrant 1 of sine and cosine, and really just sine. If you know quadrant 1 of sine, then you know quadrant 1 of cosine, right? Because it just goes in reverse. If you know both of those, then you know all the values of tangent. Now, actually knowing the values of tangent and the other trig functions will actually help you out in the long run. But if you just know these values, and that's all you really know, well, you can find the other ones because if you look at here, right, tangent of theta is just sine theta over cosine theta by definition, right? It's y over x. And cotangent is 1 over tangent, or you invert and multiply, you get cosine over sine. Cosecant is 1 over sine, secant is 1 over cosine. So, I mean, if you ever want to find a value of another trig function, say, let's say secant of, I don't know, let's say 3 pi over 4, well, the first thing I would do is use this identity that tells me that secant is actually 1 over cosine of 3 pi over 4. Okay. And cosine of 3 pi over 4, well, it's a pi over 4, so I know for a fact it's plus or minus the square root of 2 over 2. Okay. Now, which one is it? Well, we got to think of which quadrant we're in. 1 less than the denominator, that means we're in quadrant 2, and cosine is negative in quadrant 2, so this is going to be 1 over negative square root of 2 over 2. Now, we don't want to leave it like this, right? It's going to be negative 2 over the square root of 2. Now, if you were to look up the values of secant in a table or something, they would never, ever list it like this. You would never see just 2 over square root of 2. What they usually do is this number right here, where they conjugate that square root to get it out of the denominator. Okay, so these two multiply together on the bottom to give us 2. And on the top to give us 2 times the square root of 2. So that cancels, and we're just left with the square root of 2. Now this is what you would see if you looked it up in a table. Okay, but if you don't remember all the values of all the trig functions, you're not screwed, right? You can still do this as long as you remember sine, which also gives you cosine. Right? If you remember quadrant 1, you have everything. Now, if you just remember the entire unit circle, it's actually going to be a little faster for you. But, you know, it's not completely 100% necessary. Okay? Okay, having brought up the identities, now that they're in focus, let me show you some other identities that are really important. There's a whole list of these guys that you can look up in your book, or look up online, or what have you. And I suggest doing that at some point, you know, if you ever realize you need them. But there's definitely one you should take to your grave. That's sine squared theta plus cosine squared theta is equal to 1. Okay, that one's super important. These two actually come from this one. The 1 plus cotangent squared theta is equal to cosecant squared theta, and tangent squared theta plus 1 is equal to secant squared theta. Where does this come from? Well, if I take this original one, sine squared theta plus cosine squared theta is equal to 1, and divide everything by, let's say cosine squared theta, right? So I'd get sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta is equal to 1 over cosine squared theta. Wow, that's really big zoomed in. This actually simplifies. Sine over cosine, right, is tangent, so we get tangent squared theta plus cosine squared over cosine squared will give us 1, and then 1 over cosine squared is secant squared. Okay, so that is where this one comes from. And to get this one, you just divide by the other one. Here we divided by cosine squared. To get this one, you divide by sine squared. Okay, so you can get these two if you remember this one and just divide, or you could just remember, right? You start using this more often, it'll become more like second nature. These 4 identities, here's the double angle identities, and there's a half angle, or yeah, I believe that's what it's called. These identities are actually very important, especially in Cal 2. Okay, you'll see these a lot in Cal 2, especially these half angles. Okay. All right, so basically sine of 2 theta is 2 sine theta cosine theta. Cosine 2 theta is cosine squared theta minus sine squared theta. And you can play around with this one to get these two down here. Cosine squared theta you can rewrite as 1 plus cosine of 2 theta all over 2. And sine squared theta you can rewrite as 1 minus cosine of 2 theta all over 2. Okay, next up is inverse trig functions. Inverse trig functions basically kind of go backwards, right? So if you think of the unit circle, right, we have the angle theta and we have the point xy that intersects the unit circle, right? With the unit circle intersecting with the terminal side. And say, for example, sine of theta is equal to y. So basically, we give sine an angle, and it gives us the y coordinate. Right? So we give it an angle, say theta, and we make that angle, and then we, intersect the unit circle, and we get a point for each angle, x comma y, and it tells us the y coordinate. So, right, we give sine an angle, and it says, hey, okay, here's the here's the y coordinate that you would get out with that angle. Okay. All right, fair enough. Sine inverse, on the other hand, which is to the power of -1. I don't really like that notation, but it goes backwards. Okay, it gives us a y coordinate or we give it a y coordinate, and it tells us the angle necessary right, to get that. In other words, it does it a little differently. It does it kind of backwards. So if you have the unit circle and you say, okay, I want sine inverse of this y, right? Say 1/2. So we have this point here, square root of 3/2, comma 1/2. We want sine inverse of 1/2. So we plot the point, and then sine inverse will tell us which angle is needed. Right? So it tells us theta. In other words, sine inverse of 1/2, this tells us sine of what angle. Instead of theta, I'll just say what angle will give us 1/2. Now you might be thinking, well, that's tricky because there are a lot of angles, right, that can make sine equal 1/2. Right, if we go back to our unit circle, if I can find it here. Yeah, if I go back to the unit circle here, here's a y coordinate of 1/2, but here's another one over here. Right? So because of that little trick, or that little problem, we actually are only looking between negative pi over 2 and pi over 2. Okay? So sine of what angle equals 1/2? Well, theta is equal to pi over 6. Okay, so sine inverse of y only gives angles between negative pi over 2 and pi over 2. And what this actually means is that sine inverse of negative y, right, if I put in a negative angle, it's just going to give me things down here, but it actually is just negative sine inverse of y. So if you're looking for, say, sine inverse of negative 1/2, right, so what angle do I need to make sine equal to negative 1/2? Well, I know, right, that sine of pi over 6 is 1/2. That means that negative pi over 6 is negative 1/2. So this is actually negative pi over 6. So remember, with the inverse functions, we give it a y value, it gives us an angle. So let me write this down. That's sine inverse. We give it a y coordinate, it gives us an angle, and the angle is between negative pi over 2 and pi over 2. Okay. So here's the unit circle, here's theta, here's x, y, okay, and it only gives us values between here. Similarly, cosine inverse, we give it an x-coordinate and it gives us an angle. And similarly, it only gives us half the unit circle. So cosine inverse is actually between 0 and, oops, not 2 pi, excuse me, between 0 and pi. Okay. So cosine inverse, so we still have theta, but we give it an x value, and it gives us a theta between 0 and pi. So if I were to say, hey, what is cosine inverse of, let's say, well, let's do 1/2 again. 1/2. So this is basically the same thing as asking cosine of what angle equals 1/2. What angle will do that? Well, pi over 3. So this gives us pi over 3. Okay? And then finally, we have tangent inverse. Okay, and tangent inverse, again, it's a little different. Basically, tan inverse, we give it a value. That value is technically a ratio, and it gives us an angle. And just like sine, it's between negative pi over 2 and pi over 2. Right, using the same unit circle idea. But it only gives us values here. Okay, so it does help to know some trig values for tangent, but if you don't, I mean, you can think about it like tan inverse of 1. Well, what is tan inverse of 1? In other words, this is the ratio here, y over x. Y over x, that's cosine theta over, oh, excuse me, sorry, sine theta over cosine theta. And I want to know when that is equal to 1. Well, when do sine and cosine match? Pi over 4. So the trig ideas are a little tricky, okay? But again, you practice them a little bit. Basically, it's just asking you what the angle is that will give you a tangent of that value, or what angle will give us a sine of that value, or cosine of that value. Now this is actually a natural segue into solving trig functions. Right? If I say that sine of x is equal to 1/2, okay, and I want to solve for x, well, you might immediately think, well, we can use the inverse, right, and get a value, right? What is one angle that causes sine of x to be 1/2? Well, one of them is, and I call this x1 because it's our first solution. One of them, right, is pi over 6. That's our inverse. So I should write this as sine inverse of 1/2, which is pi over 6. But there's another one. Right, if we go to our unit circle, right, I have, all right, what causes x, or excuse me, sine of x to be 1/2? Well, an angle of pi over 6, but there's another one here, directly across, which is going to be the angle 5 pi over 6. So from the unit circle, we also see that we get 5 pi over 6. But we can also go all the way around from pi over 6 to get pi over 6 plus 2 pi, or maybe subtract pi over 6, go back around the other way. And actually what happens is we have an infinite number of possible solutions, because this is the graph of sine of x, if you remember, right? Sine x is a wave. And here's the graph of 1/2, and we see that it intersects a lot of times, and it's going to be an infinite number of times. So how do we, basically say how many solutions we have? Well, the way we do it is we just take these first two that are in the fundamental cycle between 0 and 2 pi, and basically just add multiples of 2 pi or subtract multiples of 2 pi. So the actual solution is going to be this pi over 6 plus 2k pi, comma, 5 pi over 6 plus 2k pi. So this is where k is basically 1, 2, 3, actually it could be 0, and also the negatives. It could be -1, -2, blah, blah, blah. So it could just all the integers are possible. So when this is going to come up a lot later, especially in chapter 4, I think it is, when we get to applications, when we're solving equations, specifically trig equations. And what I find is a lot of people are fine, say finding this one and maybe even this one, but when it comes to when they check their answers in the back and they see this kind of stuff, this 2k pi junk, they wonder what's going on. All this means is plus rotations. And why is that? Well, here we have the y value is equal to 1/2, but if I rotate 2 pi, I get all the way back around. Or if I go in the other direction, 2 pi, I come all the way around. And all of those angles will cause the y value to be 1/2, which is exactly what is going on when we're trying to solve this here. Okay. Now I want to mention, a lot of people get confused. Sine inverse is not both of these values. It's just this one. Okay. Sine inverse gives us angles that only live between -pi/2 and pi/2, but there are other possibilities that solve this equation. Okay. Now what about cosine? Let's say I want to solve cosine of x is equal to 1/2. Okay, so cosine of x equal to 1/2. Well, if I go to, well, first I don't even really need to go to my unit circle for the first one, hopefully. The first one, if you think of the cosine inverse of 1/2, what you're actually going to get out is pi/3, right? Because if you look at the unit circle, cosine is the first coordinate. The angle that causes the first coordinate to be 1/2 is this one, which is pi/3. Now, what is the other angle that will cause that coordinate to be 1/2? Positive 1/2. Over here, like when we mapped over for sine, is actually -1/2, so that's not going to be possible. Down here, we have that first coordinate is -1/2. That's not going to work. For cosine, it lives directly below. So I'll use the red for the cosine here, my cosine equation. So it's going to be 5 pi over 3. Okay, so equation 2, x2, is going to be 5 pi over 3. So the actual full solution is pi over 3 plus 2k pi and 5 pi over 3 plus 2k pi. In other words, just those two possible angles and plus any rotation you might want. And the final type of trig solution that I want to talk about that will pop up is a tangent equation. Say we have tangent of x is equal to 1. Now this is one we already looked at, where tan of x is equal to 1 is actually right here at pi over 4. Why? Because these two coordinates are equal. Pi square root of 2 over 2 all over square root of 2 over 2 is equal to 1, or you can think the y over x will be equal to 1 in this case. Okay, and so I get x, and I can write it like this, tan inverse of 1, which is going to be pi over 4. Okay, now, where does the next value, where is the next angle that will cause tangent to be 1? Well, if I map over like I did with sine, this one will give me negative 1. Right? Negative square root of 2 over 2 over square root of 2 over 2 gives me negative 1. Okay. If I map straight down like I did with cosine, once again we get a negative, because this will be negative, we'd be right here. It'd be negative square root of 2 over 2 over square root of 2 over 2, so we get negative 1 again. The only other possibility is right here, and those two negatives are going to cancel each other out, so it actually is right over here at 5 pi over 4. Now the thing to note about tangent equations, the next solution is exactly pi away. And from this second solution, the next one is pi away. So instead of having to find 2 for tangent equations, all I really need to do is add multiples of pi. Right? These are half rotations, and that's all you need for a tangent equation, is half rotations. Okay, so for sine equations, right, if sine equals some number, right, we get the first solution from the inverse, or you can just think about it, and then the next one, if we have one here, we map horizontally to get the next one, right? If x1 is over here, then x2 will be over here. Or if we end up with an angle down here, we can get the next one over this way, right? So we map horizontally with sine equations. And once we get x1 and x2, x is equal to x1 plus 2k pi, comma, x2 plus 2k pi. For cosine equations, right? Well, instead of mapping horizontally, you map vertically. So if you get an angle here, you map down to get the other one. And cosine inverse can actually give you angles over here as well, right? So you can map down vertically to get the second one as well. So you either have x1 up here, x2 down here, x1 up here, x2 down here. Right? So x1 is always going to be cosine inverse of k. Or you could just use the unit circle. The unit circle is really helpful here if you have it memorized. Now, once you have that, x, of course, is going to be x1 plus 2k pi, comma, x2 plus 2k pi. That's your rotations. Okay? And then tangent is actually much easier. Tangent of x equal to k. Well, what you're basically going to do is x is going to be tan inverse of k, then just plus k pi. You don't have to find a second one, you just add the rotations and you're finished. And that's basically how this works. It's kind of complicated, but really, you get a little practice with it, it's not really that bad. Okay, the only other thing I'd like to add here, okay, is that I said with sine inverse, if you had like a negative y in there, you could just take that out. Right, not writing it there. Same is true with tangent, right? If you have a negative y over x, you don't really write it like that, but whatever number is in there, you can actually take that out and that would give you tangent of negative y over x. So, for example, tan inverse of negative 1, that's just going to be negative pi over 4. You can just make that negative. The only extra thing you have to worry about, right, that's nice and easy, but cosine inverse, if you have a negative x on the inside, you don't just take it out. It's actually kind of strange. It's cosine inverse of x, right, plus 2 pi. Okay, so as I said, had a little camera issue there. Cosine inverse of a negative x, what you can actually do is just find cosine inverse of the x and add pi over 2. Say for instance you want cosine inverse of, let's say, negative square root of 2 over 2. Okay. Now cosine inverse of square root of 2 over 2, the positive one, is pi over 4. Right? But the negative one, right, negative square root of 2 over 2 is actually over here on the unit circle at 3 pi over 4. Now if you don't remember that, if I just take pi over 4 and add pi over 2, right, this is 2 pi over 4, what you'll end up with is 3 pi over 4, which is actually what we get here. Right, so that can actually help you out, or you can just, use the unit circle and just remember you only can get angles here up top from cosine inverse. Okay, let's look at an example that kind of puts some more of this stuff together. This is nice. We looked at some equations, but let's look at something that you may not quite know how to do, but you've got all the information to do it. So let's say I know that sine theta is 3 over 5, and I want theta to be between pi over 2 and pi. What quadrant does that make this? Pi over 2 to pi is quadrant 2. Right? So let's find cosine theta and tangent theta. Now, quadrant 2 means that cosine of theta is going to be negative, tangent theta is also going to be negative. This is very important to how you decide to do this. There are two ways you can do this problem. One is using identities, one is using a right triangle. So if I set up a right triangle, do that here, have theta, okay, and I have sine of theta is 3/5. Now remember, sine is opposite over hypotenuse if I'm looking at a right triangle, and all I have missing in this triangle is the adjacent side, right? So we can use the Pythagorean theorem, right, that the side adjacent squared plus 3 squared is equal to 25, oops, jumped the gun there, is equal to 5 squared, Pythagorean theorem, so I actually have adjacent squared plus 9 is equal to 25. Subtracting out the 9, I get the side adjacent squared is equal to 16 when I subtract 9. And now here's where a lot of people mess up. They'll say that adjacent is just equal to 4. They'll take the square root of both sides. Here's the problem. Got to be really careful, because what does cosine need to be in this quadrant? Negative. This is the problem with using right triangles, is because you don't really put negative sides on a right triangle, right? That's where you've got to be careful. So this is actually going to be plus or minus 4. And I'm going to choose, right? And we're actually choosing it here. We're actually choosing negative 4 because we're in quadrant 2. Okay. So now I have that cosine of theta. Okay. Cosine of theta is equal to, well, it's going to be the side adjacent, which I know now is negative 4, over the hypotenuse, 5. And tangent theta, well, you can either remember it's sine over cosine and just invert and multiply, or it's side opposite over adjacent, which is going to give us negative 3 over 4. However you want to do it. Right? So that's how you do it with a right triangle. If I were to do it the other way, I promise. Right? So if you want to use the Pythagorean identity, we have that sine squared theta plus cosine squared theta is equal to 1. Now if I plug in sine, which I know is 3/5, I get 3/5 squared plus cosine squared theta is equal to 1. So really I have 9/25 plus cosine squared theta is equal to 1. Subtract this over, and this is a little tricky for people because it's fraction arithmetic, but just remember 1's the easiest thing to deal with fractions. People always tell me they hate fractions, They're really not that bad, especially when you're dealing with 1, because 1 is just going to be 25 over 25 minus 9 over 25. And when you're dealing with fraction arithmetic, if you have common denominators, you just subtract like normal. So cosine squared theta, or you subtract the tops like normal, I should say, and you leave the denominators alone. So we get 16 over 25. Now, with cosine squared equal to a number, that means cosine itself is equal to plus or minus the square root of that number, which is going to be plus or minus 4 over 5. Now, which do I pick? The plus or the minus? Well, again, once again, we're actually in quadrant 2, so we're going to choose 4/5 because we're in quadrant 2. Okay, so this problem actually incorporates quite a lot of trig stuff, right? Whichever way you decide to do it doesn't matter to me, as long as, you know, each piece you do is logical. Okay. All right, so that's it on the trig review. Again, if you have any questions or you're having trouble with the homework that's assigned on MyLabs Plus, just give me a shout in my office hours or during class, and I'll be happy to help you out. But this should hopefully get you started and give you a bit of a reminder of what's going on. Okay, cheers.